This is lab number 4, and we're going to discuss how to model a Rankine cycle in Aspen. So we'll start off by going to Aspen and just selecting General with metric units. So for this model, we're just going to create the component water. Then we're going to select the methods under Methods Specifications here, and we're going to select Steam TA for this model. Right, so Steam TA, if you look at this method, it refers to Steam tables, which is great because we're handling liquid water and steam for this model. Alright, so after that we'll move to simulation. So just going back to the exercise instructions, we have to create an open single pass Rankine cycle for part A, and this will include modeling steam at 1,340 tons an hour at 4 bar, and this will be expanded in the turbine to create power. Alright, so back to Aspen now. We'll put in the material 1, which we will rename as steam. And we'll specify it using mass flow. So that's 1,340 tons an hour. 1,340. And it's all water. So mass frac is 1. Alright, and then since it's at 4 bar, let's put in 4 bar. And since it's all steam, we can say that the vapor fraction equals 1. Well, that's all done. Next thing is to put in a turbine under pressure changers. So for the turbine, it's simply a compressor, which we can select as a turbine. So get steam and connect it to the turbine. Just create the material out. Alright. For the turbine, instead of compressor, we select turbine and choose isentropic. And then key in 0.8 isentropic efficiency and 0.85 as the mechanical efficiency. Right, so we just need outlet specifications. So going back to the exercise, we see that we have some scenarios that we need to complete here. Right, so we need to change the turbine outlet and inlet pressures. But first, let's do first scenario, which is still the 4 bar inlet, but 2 bar outlet. Right, so discharge pressure is 2 bar. Then after we've completed that, you just have to check Convergence tab and change valid phases into vapor liquid, because we'll have vapor water as steam and also liquid water upon condensing. So let's see if we run it. Alright, so that's cool. Now we can look at the power generated. And the temperatures and pressures. Right, so we can see here that the steam at 144 degrees Celsius and 4 bar has expanded in the turbine to 120 degrees Celsius and 2 bar. And we have the work here, but to see the results for certain, we can go right-click results and see the work generated or power generated in kilowatts. Right, so we can see there it's 31,082.3 kilowatts or 31 megawatts. Right, so that goes in there. Okay, so we'll just go through these three scenarios quickly. So for the second one, we'll change turbine outlet to 0.4 bar, and then the third one will change inlet pressure to 10 bar, and fourth, inlet pressure to 30 bar. And we'll see how the power changes. So second one, we'll change the specification of the compressor from 2 bar discharge to 0.4 bar. Right, next. Okay. And then we'll see the change. So from 31 megawatts, it's now 94 megawatts. Next change is inlet pressure of 10 bar, so I just need to change that from 4 to 10. Now we see it's 131 megawatts. And lastly, we'll do 30 bar inlet pressure. And we'll get different power generated 173 megawatts. So let's put it in there. So in here we can see a progression going from just 31 megawatts to 173 megawatts. But of course, if we change the inlet pressure, it requires either more heat to increase the pressure or a pump or a compressor, which is not likely. And then if we change turbine outlet from 2 bar to 0.4 bar, we need to design for a depressed pressure of 0.4 bar. So those are good considerations when designing a turbine. Right. So from the open single pass, we'll go to a cycle like this one. So it goes from the boiler to the turbine to a condenser like this and to a pump. And so far we've put in this stream over here, this turbine, and this stream over there. So we just need to add a condenser, a pump, and a boiler. Alright, so condenser, we'll just use a simple heater like this, and a pump. Another simple heater like this. Okay. Then we attach this stream, reconnect destination to that. make a new material coming out from that to the pump, connecting the pump to the boiler, and finally connecting this first stream to the boiler. Right. For the sake of order, we'll flip that and we'll rotate that. Okay. Right. Now to specify the equipment. So just going back to the exercise. Right. So we'll specify turbine as 2 bar, condenser, pressure 1 bar, vapor fraction 0, because we're condensing the vapor back to water. The boiler we set at 4 bar, vapor fraction 1, because we want to evaporate all the water. And then the pump discharge will just be 2 bar. So it's just moving the liquid from the condenser along to the boiler. All right. So first the condenser. So instead of temperature, we'll specify vapor fraction and pressure. Pressure is 1 bar. And vapor fraction is 0. And last one is a pump, which will specify discharge pressure of 2 bar. So for the heater, we'll set pressure and vapor fraction. Pressure is 4 and vapor fraction is 1. After that, next, and we can run it. See the result. Right? So we can see that the results are that steam at 144 degrees Celsius and 4 bar expanded to 120 degrees Celsius and 2 bar. Then the condenser condenses the steam from 120 and 2 to 101. And the pump increases the pressure from 1 bar to 2 bar. And the boiler increases both the temperature and pressure from 100 to 144 and 2 to 4. And you can also see that the power produced here in kilowatts, it's 31 kilowatts, 31,000 kilowatts, which is 31 megawatts. So 31 megawatts, but the power required from the pump is 38 kilowatts. So that's fairly small compared to the power produced. So the load in pumping the water is not too big. Right? That's a fairly efficient process, I think. Right? And we have to look at the condenser duty. Look at it in kilowatts. It's 826,000 kilowatts, or 826.8 megawatts. Right. Right. And we can see here the heat required for the boiler. Again, in kilowatts, it's 863,000 kilowatts, or 863 megawatts. Right. So that's a lot of heat power, or heat. So if we have to supply 827 megawatts of heat, how are we going to do that? So if you remember from the lab number 2, where you modeled a combustion process and a heat exchanger that represents a boiler, that's how it is. So we won't do it in detail here, but um, if we put in an R stoic there, fuel line there, and then flue gas there. And then instead of using a simple heat exchanger like that, we'll use heat exchanger that has 4 streams, right? And then the flue gas stream will just connect to the hot side, while the cold side will just be your water stream. Okay, so we're reconnecting and making new, or reconnecting existing streams. Right. So 5, 6, 7, 8 is part of the combustion and flue. Flue gas will be composed of carbon dioxide, carbon monoxide, water, depending on your model. So that just usually goes out into the stack, or if you have heat recovery, goes through those. But the main idea is the hot flue gas boils the water there into steam. Right. I won't run it because I don't have the components for the fuel, but that's the general idea. Right, so that's it for the Rankine cycle, and till next time.